Not totally bad. You know, if you're not involved in testing, you got more free time now because there's no classes on Tuesday and Wednesday for a couple of weeks in a row. And for teachers, it's chaotic even longer because after next week, the week after that, junior high is Atlas testing. Now that doesn't involve all of us teachers because a lot of us like I don't have any junior high classes. I will have my normal classes with you guys on that week. But for the teachers that do both, like some of our teachers do junior high and high school classes, it's going to affect them. And so be looking for emails for some of your teachers after next week that may have their classes affected by junior high Atlas testing 2 weeks from now. So you may have some of your classes that get rearranged, but not all of them because some of us won't be involved in the junior high testing. So, all right. Let's see what we got this week. On the right screen? Yes, I am. I am on the right screen. Let's put this up, take a look, see what life looks like this week in Algebra 3. All right, here's what it looks like. Let's go to the grade screen. That's where we always start. If we scroll down, we'll see that we are ready for 8.04 complex zeros. Complex zeros. Notice this goes down to basically the 10th. The 10th is the last week seniors will be here, and there's a lot of seniors in this class. Not everybody, we have several juniors in this class as well, and we will have something to do after the seniors are gone, but the seniors will be done by the 10th, and senior finals are on the 11th and 12th for any finals you have to take. That's that Monday and Tuesday. So, but the last week we'll wrap this up by the last week there. But we have complex zeros this week. And then next week we have 2 lessons. And then we have, well, we'll see. The practice test or maybe not. Graphs of rational functions for the 3rd week. But complex zeros, just 1 lesson this week. So we should be able to get through this without any issues whatsoever. Hopefully you're already done with the first 3 assignments. I know I've graded several of those, so you guys are doing good. Just got to get caught up with this week. With a Tuesday or a Thursday. All right, here's our scenic overlook. Let's take a look at this. A difficulty that we have avoided in determining real zeros for polynomial functions is some quadratic equations do not have a zero, which is a real number, right? When we graph it, a lot of times it will not touch the x-axis. We're like, oh, this doesn't have any zeros. Well, that's not totally accurate. It does have zeros. They're just imaginary zeros. So that's what we're looking at this week. The most common example is x squared plus 1 equals 0. Let's go ahead and throw that on a graph real quick, just to remind us of what we're doing. Graphing calculator. X squared plus 1. Look at that. It does not touch the x-axis. So you're like, this does not have any zeros. They are imaginary zeros. There's no real number that when squared gives us a result of -1, right? If we were solving it algebraically. So to allow a solution, the mathematicians assign a value of the square root of -1 called the imaginary unit or imaginary number designated as I. I equals the square root of -1. And I squared is actually a real number, -1, because square root of -1 times the square root of -1 is -1. Complex numbers are written in the form a plus bi. So let's look at the definition. The definition of a complex number. For real numbers a and b, the number a plus bi is a complex number. And we say it's complex because part of it is real and part of it is imaginary. If a equals 0, which a can equal 0, and bi, b is not equal to 0, bi is an imaginary number. So we can see that the set of real numbers and the set of imaginary numbers make up the set of complex numbers. So let's just put some notes down about that. So let me get that. There's some Algebra 2 notes. Let's get some Algebra 3 notes. So complex numbers. Just so we make sure we understand them. And it's not the first time you've seen complex numbers, but it's good to do a little review. A plus BI, where, let's see, it's out of my way. This is the real part. The A is the real part of the imaginary number. And this is the imaginary. And the main thing that's imaginary is the fact that it has the I. And we know that I equals the square root of -1. So I equals the square root of -1. So complex numbers. So very simple. We have them in our notes just to remind us. So A could be 0, right? We could just have BI. Could have just like 7I or 3I or something like that. If B is 0, it's not an imaginary number. If that's gone, you've just got a real number, right? So if B is 0, you don't have a complex number. A could be 0. You could be no A. You just have some number with an I. But if B is 0, it's not an imaginary number. It's not a complex number. It's just a number. So operations. The rule for equality of complex numbers states if you have two complex numbers, A plus BI and C plus DI, written in standard form, are equal to each other. A plus BI equals C plus DI. Let's talk about when that is a true statement, because this is written very fancy in college terminology, but it's really so simple. It's saying if A plus BI equals C plus DI, this is only true when A equals C and B equals D. Let's see exactly what they're talking about. A and C should equal each other. Okay, that kind of makes sense. That yeah, if we're saying those are equal to each other, and B and D would have to equal each other. So if we have uh, 3 plus 2I, what number would be equal to that? Well, this says these are only equal when A equals C. The real numbers have to be the same. So is it really this easy, Mr. Brock? 3 plus DI would equal 3 plus 2I would equal 3 plus 2I. Yeah, it's really that simple. This is not a trick question. Uh, it's written very mathy, very college level thing. A plus BI equals C plus DI is only true when A equals C and B equals D. It's like, what does that mean? Well, that means the real numbers have to be the same and the imaginary numbers have to be the same for those to be equal. Well, that was pretty easy. Yeah, it really is. It really is that simple. Um, but in math, think about when you had geometry and you had to do all those proofs. On the proofs, you had to say every little simple thing, even though it's like, well, I don't ever write that because we know that. That's, 1 equals 1. I don't have to write 1 equals 1. Well, in math, when you're writing down what things equal, or you're writing a proof, or you're writing an equation, why is this equation true? You have to put all the little things that we know is true. Yeah, I know that 3 equals 3. That if this is 3, that has to be 3. But in math, you can't just put those assumptions out there when we do all this stuff. So yeah, it's true if and only if. Oh yeah, I guess I should do that. True. In math, they write if like this. This is true if and only if. Instead of when, I should say that. We just put that in the place of the when. There we go. There, we're going to fix this. True if you spell it with two F's, that's a math thing. A plus BI equals C plus DI. And that's true if and only if A equals C and B equals D. If A equals C but B does not equal D, this is not true. Well, yeah, if this is 3 plus 2I equals 3 plus 4I, they're not the same. They're not equal to each other. If and only if. Yeah, let's write that down. If and only if. That's what that means. If and only if. I don't know what happened, but my writing's pretty good today. You're probably like, who is this guy writing for you, Mr. Brock? You got somebody else that's using their hand over there. No, my writing's doing well today. It's amazing. We'll enjoy it while it lasts. So here's the rule for addition and subtraction of complex numbers. It says, okay, A plus BI and C plus DI are two complex numbers written in complex form, which is the real plus the imaginary. The sum and difference is defined as followed. Sum of A plus BI equals C plus DI is you add the real part and you add the imaginary part. Well, that's probably good to do in our notes here. So let's talk about addition and subtraction. Addition and subtraction. So if we have A plus BI plus C plus DI, that would be A plus C, because we can only add the real to the real, plus B plus DI. So let's write an example of that. If I've got, let's even do a negative. Negative 2 plus 3I. And I'm adding that to 5 plus 2I. A plus C. A is negative 2, C is 5. So this would equal 3, because negative 2 plus 5 is 3. Plus, we add the B and the D, 3 and 2. And we can kind of highlight that to emphasize what we did there. So we understand in our notes what we did. Very simple. We can only add real numbers to real numbers. We can't add the 2 and the 3 here, or the 5 and the 2, or the 5 and the 3. We can't do that. We can only add real numbers to real numbers. And in the same method, subtraction works the same way. If we have, I'll do the generic form first, minus C plus DI, we would do a minus C plus B minus DI. So if we have negative 2, we use the same ones. Minus 5 plus 2I. Negative 2 minus 5. So this would be negative 7. 3 minus 2 plus I. Because it's just one I, right? One. So negative 2 minus 5. And then we have 3 minus 2 is just 1. So it's not hard as long as you remember you have to keep the real numbers separate from the imaginary numbers. So don't overcomplicate this. Don't look at all this and go, oh, all these A's and B's and C's and D's. Oh my gosh, this is really complicated. This is really hard. This is, boy, with some high level math. It's really pretty simple. Just keep the real numbers with the real numbers. Then you're doing elementary school, right? We're doing -2 plus 5. And we're doing 3 plus 2. We just put an I on the end of it. So think of it like a variable X or something, right? Like 3X plus 2X. So you just have to make sure, keep the reals and the complex separate. Some of the properties for real numbers are also valid for complex numbers, like the associative property of addition and multiplication, the commutative property of addition and multiplication, and the distributive property of multiplication over addition. So these properties and the definition of I, and knowing that x plus I times x plus 1 times x minus 1 equals x squared minus 1, we can divide and multiply complex numbers. So they will give us some practice examples to do here, and then we can check our answers. So I'm going to write these down so we can just do all of these. Let's work our way through these. Addition. Okay, we've already looked at addition. This is really simple. We just have to keep the real numbers with the real numbers and the imaginary numbers with the imaginary numbers. So 5 plus 6. Negative I, so that's negative 1I, plus 3I is 11 plus 2I. All right. So far, so good, Mr. Brock. It's pretty simple. 5 minus 2I minus 7 minus I. So 5 minus 7. Real minus real. Negative 2. Negative 2I minus a negative 1I. So that's a 1I, right? Just I. Minus a negative. Minus a negative. That means we're adding an I. Negative 2 plus 1 is just negative 1I. So negative 2 minus I. This we're multiplying. Remember, when we multiply, we have to distribute. So we got to distribute the 5 to both terms. 5 times 6 is 30. 5 times 3I. We can multiply a real number times an imaginary number. That's just 15I. Multiplying. Now we have to distribute the second number. Negative I times 6 is negative 6I. Negative I, here's the interesting part. This is where it gets interesting when you have complex numbers. Negative I times 3I is negative 3I squared. Oh, we have an I squared. What's I squared? I squared, since I times I is the square root of negative 1. We're taking the square root of negative 1 times the square root of negative 1. What is the square root of negative 1 times the square root of negative 1? It's just negative 1. Because the square root squared, when you have a square root and you square it, those cancel each other out. So whatever's inside comes outside. Whatever this is just comes out. So this negative 1 comes out because square roots squared cancel each other out. So this is negative 3 times negative 1. That's what this is. So we have 30 plus 15I minus 6I is plus 9I. Negative 3 times negative 1 is plus 3. Then we have 30 plus 3. So this is 33 plus 9I. So when we multiply those together, that's what we get. Don't forget, you get those middle terms when you have to multiply two binomials together. Don't just multiply 6 times 5 and I times 3i, because you'll be off. Looks like that. Okay, this one is divided by. So which means we're taking 7 minus I, and we're dividing it into 5 minus 2i. Like, oh, that doesn't really work, Mr. Brock. No, it's going to be something really nasty. I want to see how they did that, because I have not divided complex numbers like that in a while. I think they're just going to have the answers. So I'd like them to have some work, but I'm afraid they don't. Oh, it gets into fractions. 11 plus 2i, that's what we had. Negative 2 minus I, that's what we had. 33 plus 9i. But 37 fiftieths minus 9 fiftieths I. Oh, over 50. I didn't want to try to divide that, but that you can divide them just like you could divide, just like we would divide, 5 minus 2x divided by 7 minus x. It would work the same way as just polynomial. You treat this separately than you treat the 2x separately than the 5. You treat the 2i separately than the 5 there. It works the same way. But I'm not going to get into all of the fractions and all that. That's not the point. The point is it works the same. I'm not going to get into the whole rabbit hole of doing that one. Plotting complex numbers. All right. You're thinking, how would I graph this? For the most part, we will not deal with complex numbers in applications. However, it would be good to be able to plot complex numbers. To do this, you need a graph area called a complex plane. Now, we use this graph for x and y, but imaginary numbers also have a z. It's kind of like three-dimensional. So we'll use the horizontal axis called the real axis, vertical axis called the imaginary axis. And for complex numbers, a plus bi, we'll plot the a value along the real axis and b along the imaginary axis, because you're going to have a value of an imaginary axis. So this just shows an example of declaring an imaginary axis. And so I guess it would be actually up here. But we do need to cover, the reason we couldn't do this is we haven't talked about complex conjugates. Let's talk about conjugates. Complex conjugate. Complex numbers have a conjugate. And you're like, what a weird word, conjugate. Let's talk about 5 minus 3i. Okay, so this is an imaginary number. The conjugate of this number is 5 plus 3i. There's only one difference between a number and its conjugate. And you're like, okay, what good is the conjugate? Well, if you multiply a complex number by its conjugate, it's no longer imaginary. Like, what you say, Mr. Brook? If you multiply a complex number times the complex conjugate, it's no longer an imaginary number. Really? Yeah, let's try that. I'm going to multiply 5 minus 3i times its conjugate of 5 plus 3i. And we're going to see what that equals. If I multiply a number times its conjugate, we got to distribute 5 times 5, 25. 5 times 3i, 15i. Okay, so I've distributed that. Now I have to distribute negative 3i. Negative 3i times 5. Negative 3i times 3i. Negative 3 times negative 3 is negative 9. I times I is I squared. Oh, what did we say about I squared? So this is the same as negative 9 times negative 1 because I squared equals I squared, which is negative 1. Square root of negative 1 times square root of negative 1. So this is 25. These cancel out. Plus 15i, negative 15i. So this is 25 plus 9. That's a real number. There's no imaginary part. The imaginary part went away because I multiplied it times its conjugate. Here, I'm going to go back and let's play with this. I'm going to see if I can erase that. This is how you delete on paper instead of a computer, right? You get one of these deleters. So this said we could divide 5 minus 2i, 7 minus I. So the question is, how do you divide complex numbers? You multiply by the conjugate. 7 plus I. 7 plus I. I'm multiplying by the conjugate over the conjugate. 7 plus I. So this is just 1, right? If I do 2 over 2, that's 1. If I do 11 over 11, that's 1. Well, if I do 7 plus I over 7 plus I, that's 1. So I'm just multiplying by 1. But what happens is when I multiply these two, let's multiply 5 minus 2i times 7 plus I. Okay, so this will be the numerator. 5 times 7 is 35. 5 times I is 5i. Negative 2i times 7, negative 14i. Negative 2i times I is negative 2i squared. So this is 35. Oh, losing it. 5i and negative 14i is negative 9i. And this is plus 2 because it's negative 2 times negative 1. So I've got 37 minus 9i. That is the numerator. Over, let's multiply this times its conjugate. 7 minus I times 7 plus I. 7 times 7, 7 times I. Negative I times 7 is negative 7i. Negative 1 times, negative I times positive I is negative I squared. These cancel out. Negative I squared is negative negative 1. So it's 49 plus 1. That's what it equals. When I divide this, I get 37 minus 9i over 50. Let's see if that's what they had. 37 minus 9i over 50. You could also split it 37 over 50 and 9i over 50. But 37 minus 9i over 50. Because you multiply by its conjugate. When you divide, you multiply by the conjugate for the denominator, and that will get you there. So that's the overlook of the lesson. Let's go through here and see if there's anything they covered down in the lesson that's not in the overlook, because conjugates should have been over here, up here in the overlook. Complex numbers, this is just examples. Negative 6 is not a complex number. 5i is. Square root of 5 is not. Negative 7i is. 5 halves I plus 2/3. That's a complex number. Negative 2 plus 3i. That's a complex number. All these are complex numbers. It's saying negative 6 is an example of a complex number, but the B part is 0. Here, A plus BI. The real number A is the real part. B is the imaginary part. Standard form A plus BI. So we went over that. Here's that x plus yi equals 2 plus 5i. If and only if x equals 2 and y equals 5. And yes, there's actually a problem like that in your assignment this week, saying what x and y is. This talks about adding and subtracting them. We went over that. The additive inverse, let's just say you can add the negative. Multiplying complex numbers. Okay, we talked about multiplying them together. You get that I squared. That's where it's the only tricky part. Remember, you get the I squared. Well, this talks about raising a complex number to a power. Well, that would just be multiplying itself. Like, if you square it, it just means you multiply it times itself. If you cube it, you multiply it times itself 3 times. Complex conjugates, as we were just talking about, in division. So to divide it, you multiply by the conjugate of the denominator. So that's the examples they throw in that. Complex solutions of quadratic equations. Well, that's when you solve that and you get that negative, you get that I. So it talks about the discriminant back from the quadratic unit where we talked about that. Solid quadratic. Okay, that is all of the lesson. So most everything is all right here on one page. The complex conjugate, understanding you can only add the real numbers to the real numbers, the imaginary to the imaginary, and then adding and subtracting all work the same way. Adding, subtracting, add the real numbers, add the imaginary numbers, subtract the real numbers, subtract the imaginary numbers. And this is true if and only if the real numbers are the same and the imaginary numbers are the same. That's what that's saying. This is true if the real numbers and the imaginary numbers match each other. Let's look at the assignment. This was pretty short this week. Not bad at all. Write the sum or difference of the standard in the standard form a plus bi. So it's saying this might be addition, it might be a subtraction. So you got to check your problem. Mine is subtraction. So I have to subtract those and give the answer. Write the product. Products when you multiply. So multiply those together and give us the answer. Find the product of the complex number and its conjugate. Oh, now here's a good one. They didn't give you the conjugate. They just said multiply this times its conjugate. The conjugate is the exact same. You just change the sign. I should only have to give you this. And then if I give you this, you automatically know what the conjugate should be. If I give you negative 6 minus 11i, what's the conjugate? What's the conjugate? It's negative 6 plus 11i. You don't change the negative 6. The real number is still the real number. The only thing that changes is the sign in between the two terms. All right, so understand that on the conjugate. We're not changing the sign of the negative 6. We didn't change the sign of the 5. We only changed the sign of the imaginary part. Instead of subtracting, we're adding. Conjugate. So on that assignment, 3 plus 3i. You can already know what the conjugate is. And write the expression in standard form. Standard forms means you don't have imaginary number in the denominator, which means you multiply this just like I did right here. Multiply it times the conjugate, top and bottom. Make sure it's a plus because this is a minus. So do this. This is standard form. It's not standard form to have imaginary in the denominator. You do not want an imaginary number in the denominator. So you have to multiply the top and bottom by its conjugate right here. And they split it up. They said, okay, so each part you put the fraction. So like on ours, we could have taken 37 over 50 minus 9 over 50i. These are the same. When you have a denominator, you can put the denominator under each term separately if you want to, which is that's how they're showing it in Buzz on the answers. These are the exact same. 3750 minus 9 over 50i. So, and then here's the only one you have to type anything. Find x and y that make this equation true. Negative 3 plus yi equals x plus 6i if and only if x equals what and y equals what. This should be the easiest one on the whole assignment. All right. Questions on that? Questions? All right. I'm going to kind of make it a little lighter this week just because we have such a short week. I'm going to look at next week's and see how overpowering it is because I had 2 scheduled for next week. But again, it's a short week. We're not going to meet until Thursday again next week as well. So I'll take a look at it and see if it's too overbearing. I'll try to rearrange, but we're running out of time, so I can't really rearrange a lot. But easy week this week. Just a short lesson, 5 questions, and then you can go tackle your weekend starting Thursday. So, all right, guys, have a great week. Hang around if you got questions.